Now, we also mentioned that another thing that we may be interested in connection with estimating a population parameter is the sample size that we need. We don't want to do more work than we absolutely have to. And also remember that the more accurate we want our results be, the larger the sample size we will need. Okay, so our sample size is closely connected to the accuracy that we need. So every time you have to basically figure out, can we afford to sacrifice a little bit of the accuracy for the to get a smaller sample size. All right, so in order to figure out our sample size, we need to specify the confidence level, and this is the Z value, the critical value that corresponds to that confidence level. We are getting it from the normal distribution table, the Z table, not the T table. Now, we also need a standard deviation of the population and the margin of error that we can allow. Again, the more accuracy, the less the margin of error is. Okay, here's an example. Use the given formula and the given margin of error, confidence level, and population standard deviation to find the minimum sample size required to estimate an unknown population mean. So margin of error, or just error, here is 0.25 seconds. The confidence level is 99%. So that means that alpha is 0.01. And our sigma, or the standard deviation of the population, is 5.40 seconds. Okay, with this information, we can actually find our sample size. So, but first, we need to find our critical value of Z of alpha over 2. So we have in the middle 99%. So alpha over 2 in the right tail, we're going to just have the half of this area. So 0.01 divided by 2 will give us 0.005. So 0.005. So this Z has a tail area, cuts off a tail area of 0.005. So we're gonna go into our normal calculator and calculate that critical value. So we would go to stat calculators and then normal, and we get our standard normal distribution as Z distribution with 0 for the mean and standard deviation 1. In the tail area, we want to change this sign to greater than, and then for the area in that right tail, we're going to put in 0.005. So this gives us a Z value of 2.576 rounded to 3 decimal places. All right, now we can use this value in our formula. So N is equals to OZ, which is 2.576 times standard deviation of the population, which is 5.4, divided by the margin of error, which in our case is 0.25, and we're gonna square that value. When we put all of it into our calculator, we're going to get 3,105.609,984. Okay. Here's the thing though, when you're asked to find a sample size, we want a whole number. We don't want a decimal like that. So you would always round up, and this is important. Think about it. What we found is the minimum, the absolute minimum sample size that you must get in order to have this level of confidence, the 99% confidence. If we lower the sample size, we're going to lower the accuracy, and 99% confidence level will not hold up. So we can only increase this number. We can never decrease it. So that is why we're always going to round up our sample size. So sample size is 3,106 for this specific problem. So always round up. I just want to reiterate again that we don't use our regular rounding rules for the sample size. So even if we had 3,105.0001, we would still give the sample size as 3,106. Our N should always be higher or equal to, if we get a whole number here, or higher to the actual decimal value that we got.